In the first presentation on stream power and bedrock erosion, I left off with these exact two questions. So first, what is the rate of bedrock erosion? That's ultimately what we want to answer. The related question then is, what is the rate of potential energy to kinetic energy conversion? And we know that some of that potential energy will turn into heat, and some of it will be used to erode bedrock. And in order to understand that, let's start out with that first point of how much potential energy will be converted into other types of energy, kinetic energy or mechanical energy, so heat in general. Well, what we can do then is to describe something called stream power, which is going to give us the rate of that conversion. And I'm first going to define stream power in words, and then we're going to define it mathematically. So stream power is the rate, and so once you see the word rate, you can think per time, of potential energy loss in a channel cross-section per unit time. So underline channel cross-section per unit time and potential energy loss. So basically everything that's not just a word connecting some other words. So when I say cross-section, here's what I mean. So we have a river channel like this. Maybe that's not going to be a good angle to draw it. All right, yeah, that'll do. And in fact, what I'm going to do is use a couple different colors. We can actually be a bit creative. So we can have a nice little blue water surface. And I'm going to have a nice little blue profile around here. So this is our river. And just to remind you of the symbols that we commonly use, this is a triangle to indicate that that's a free surface. And so this whole area in here is all water. Maybe I'm going to do this. Hey, look at that. That looks way more like a river. All right. I'm going to put that one in the back pocket and save that for when I try to remember to be a not terrible artist at some point. If you guys remember my attempt at a bear, not very good. All right, so here's a river channel, and the cross-section is this thing right here. It's at a single, point downstream. What is, you have this like width and depth, and so the cross-section then would look something like, this, where we have, this flat water surface over it. And so this is going to be a cross-section of a river channel. And it exists in a very, very thin layer in the downstream direction. I'm just going to call this delta x is the width of this cross-section. And you can also think of it, if you prefer calculus, as dx. So next thing is a potential energy. So we know that P in this fluid is equal to rho times the control volume, and so this is just your mass, times G, times Z, which is the elevation. And power is the rate of dissipation of that over time. So then if we try to then turn this potential energy into a power, what we need to do is define that. So omega is stream power. And just the general physics-based definition of what a power is it is energy per unit time, right? So for example, your light bulb might be using a certain number of watts, and a watt is a unit of power, and so that's how much energy is being consumed by that bulb in SI units every second. So we'll have, so in other words, if you have a 60-watt old incandescent light bulb, that is using 60 joules of power, of energy, every second. And so then the power is 60 watts. And so we need to think about how we can take this potential energy and convert this to energy per unit time. And so what I'm going to say is that stream power is going to be equal to the change in potential energy over the sum delta x, so that's going to be this cross-sectional distance, because we need to have some sort of distance, right? Otherwise, because if we just say stream power is just over some arbitrary distance, the longer the distance we pick, we might get a different change in potential energy. And then over delta t, which is this change in time. And something I'm just going to do right here is just put a minus sign in front of this. And the reason I have that minus sign is because we're interested in what is converted into energy that can do work on the channel. Right, so what we want to know is actually what the negative sign of potential energy is and what can be done with that energy. So, bearing with me for a second while I change colors again. So what is this then? So if we have this potential energy here, we can then say that change in potential energy would be, minus rho times volume times g times delta z, so some sort of change in elevation. And then on the bottom, I'm going to actually separate these two out. I'm going to put delta x over here on the left-hand side, and I'm going to put delta t over here on the right-hand side. And so there's a reason that I'm doing this. So let's see, it's a question. Maybe I'll make these comments in gray so this is going to show up a little bit better. So why did I separate this equation like this? Well, a few of you might remember from the last lecture that I defined this control volume as V equals delta X, delta Y, delta Z. So you can have if you have a box like this, and maybe just with like some, little kind of nearly invisible lines in the back, we have delta X, delta Y, and delta Z, and this is our control volume of the fluid. And so therefore, what I can do is substitute this in and get that this also equals minus rho delta X, delta Y, delta Z, G over delta X. And hey, look, lo and behold, these guys cancel out. And then on then next to that, I have this delta Z over delta T. And what I want to know then is how quickly in time, so what is the rate at which the water is dropping in elevation vertically? So this is just going to be vertical distance per time. So let's think about how we might go about measuring or calculating that. And in order to do that, I'm going to draw a inclined plane like we have so often for rivers. So we have this inclined plane right here, and we have over here, I'm going to draw on it this imaginary horizontal line and say that it's sloping down at some angle alpha. And that on top of this plane, so this is, in spite of its green color, this is actually a river. So, you know what? Gosh, that was a terrible color choice. Let's just go with blue. All right, we have a sloping river. Then we're going to go back. It has an angle alpha with respect to the horizontal. And water is moving down slope and down channel at a velocity u bar. Velocity u bar. And then if I look at just what this slope is, so we have rise and run right here in this little diagram, and that is just going to be the slope. Also, you can think about the fact that u bar can be partitioned into a couple different velocities. And this one here is going to be, I'm going to call this u bar sub vert. And so that's going to be the u bar in the vertical direction. And we can also just call that u bar of z. How about that? That's going to be a little bit easier to remember. All right, great. So u bar of z. So what is this value of u bar of z? Because actually, since this is the down slope, down channel velocity, if we get this u bar of z, this is literally just going to give us the change in elevation over change in time of the water. Well, fortunately, we have some trig functions for that, right? So here, if you think about this, we have a triangle. And so the hypotenuse of this triangle is this u bar term. U bar sub z is this. And over here, we just have alpha. And so we have opposite over hypotenuse. So therefore, we know that sine of alpha is going to equal the opposite, so u bar sub z over u bar. Typically in rivers, this angle alpha is small, a few degrees or less. And so with this, we have this nice little advantage that we can use the small angle formula. So if alpha is small, then we actually know that cos alpha is approximately 1. And also then that sine alpha is approximately tan alpha, and tangent of alpha is just equal to the slope. Let me rewrite that so it looks better. There we are. Is equal to the slope. So therefore, then I can pop the slope into this equation and say that the slope is just equal to, scrolling up, that u bar sub z at the top over u bar. And therefore, u bar sub z is just equal to u bar times the slope. And if we think about this, just to do a quick idiot check, this makes sense because if there's a certain velocity going down channel and the channel slope is small, then much of that velocity is going to be in the horizontal, but some of it will be in the vertical. And a typical, let's say, gravel bed river slope is something like 1%, so 1 part in every 100 of that river's velocity will be bringing that water vertically downwards. Okay, great. That makes a lot of sense. So now what we can do is go back to our stream power equation and plug it in. Since it's lost off the top of the page, I'm just going to rewrite this right now. So I'm going to say that omega, which is stream power, is equal to rho delta x, or sorry, we cancel that one out, delta y, delta z, times g, times delta z over delta t. And u sub z is equal to delta z over delta t. And therefore, we can just simply substitute this in and say that omega is equal to rho delta y delta z, g, mean velocity, slope. So the next thing that we do is we invoke something that we call the rectangular channel approximation. And in this, we say that our control volume is not just some random volume, right? So we had this delta x, which was the distance downstream through the cross-section, but we've been talking about the full cross-section the entire time. And so what we're going to say is that we're thinking about a river channel where we can approximate it, just like we did when we discussed flow velocities, as having a rectangular base and vertical walls. And this, of course, is not the same thing as a river in nature, but to be honest, a river in nature, even if it looks like it has a sloping bed and banks, is really, really close to a rectangle because of how much wider it is than it is deep. So this is not a bad approximation. And so with that then, we can say that we have delta z here and delta y here. And delta y and delta z are the cross-sectional area. And so let's just imagine that then coming out at us, we have u bar. And therefore, we can say that the discharge going through the river, so this is discharge, is just equal to delta y, delta z, times u bar. And so now we can substitute this in and make the whole stream power equation look much neater and nicer. So we now have omega is equal to rho. I'm going to write g, and then I'm going to lump delta y, delta z, and u. So I have q, and the last term is slope. And this, everyone, is the equation for stream power. And I'm just going to, as a little reminder, note that basal shear stress in the river is equal to rho g h for depth, slope, and so that's also pretty similar, right? And I didn't explicitly mention it this time, but the way I was able to remove the kinetic energy conversion, or potential energy conversion into kinetic energy related to flow velocity or sediment motion. And so I'm just going to scroll back up here into last time's notes. So the way I was able to say that flow velocity and sediment transport are not going to be major points of conversion of that energy is by using a uniform flow approximation. And steady, so steady, uniform flow, meaning that there isn't any change in that flow with distance downstream, and that there also isn't change in time, and so therefore the real important one is this uniform bit right here. And this is the same thing as the depth-slope product for steady uniform flow, so I'm just going to make a big little note of that. And steady uniform flow conditions persist throughout most reaches of most rivers. It's a really good approximation as well. Finally, we're going to think about how we apply stream power for erosion, because what we can see here is that if we're just relating it to discharge, if this width, the delta y over here, starts to become really great, we're going to have a really large stream power. But when I think of wide rivers, I think much more of like a big lowland river. Think about the meandering Mississippi in the south of the US, or think about a big old braided stream. So those rivers are not really eroding really rapidly into bedrock, are they? So what's the deal? Well, first off is the fact that, for example, the braided stream is blanketed in sediments. But more related to the argument I'm trying to make here is the fact that we actually have to normalize per unit width, because just because a flow is wide doesn't mean it's going to be effective at eroding into bedrock everywhere. What we want to do is have a way of balancing the stresses or the power at every single point, right? And so that's why, for example, in this shear stress equation on the right, we have h, so just the flow depth. And so how can we make a similar transformation for the stream power? Well, you guys have probably already figured it out. What you want to do then is say that this is going to be, this is, by the way, little omega, whereas that was big omega. So this is omega, and so this is the unit stream power. Wow. Come on, handwriting. And that unit stream power is equal to big omega per width. And so then we can set that equal to rho g q over b, so discharge per unit width, times slope, which then equals, by the definition of what big Q over b is, rho g little q s, where little q is discharge per unit width. I'm going to specify water discharge per unit width. And so it is now this discharge per unit width, this small omega, that we will start using in the next video to describe the rate of bedrock erosion.